The last couple problems that we looked at were relatively easy to find error bounds for the functions because the functions sine and cosine had nice patterns for the derivatives, and so it was easy to bound the derivatives by 1. In general, most functions don't have derivatives that behave that well, and so most of the work for bounding error is going to be in finding a good control of the derivatives of the function. And so let's look at an example. Let's say that we're trying to estimate the natural log of x using Taylor polynomials that are centered at x equals 1. And in particular, let's say that we want to approximate the natural log of 9/8 to within 3 decimal places. In order to do that, it would be helpful to have the full Taylor series written down for the natural log so that we could just take some of the terms at the beginning and use those as Taylor polynomials. On a previous lecture, you already computed that the natural log of x has this Taylor series expansion, which is just minus 1 to the n plus 1 times x minus 1 to the n, all divided by n. So we're going to take the first few terms of that, plug in 9/8, and that should give us a good estimate of natural log. But we want to know how far out in the series do we need to go before we get this good estimate. And so in order to figure that out, we'll use that same error-bound formula, which is that the absolute value of our error is less than or equal to the maximum of the n plus first derivative. And then I have to specify the range that I need to maximize over. And so in this case, as per usual, I need to consider all x values between the center of the series, which here is 1, and the value that I'm plugging in, which here is 9/8. And then once I have that maximum, the other terms here are going to be the difference between the center and the value I'm plugging in, raised to the n plus first, and I should put this in absolute values, and then divided by n plus 1 factorial. And so like I just said, the hard work about finding this bound or simplifying it is going to be to simplify this maximum of the derivatives. And so in order to do that here, I'm going to do the same sort of procedure that we used to find Taylor series before, which is I'm going to write down a table of the derivatives and then the maximums of those derivatives. And hopefully there'll be a pattern for the derivatives, but if there's not, then I can just write out a whole bunch of them and hope that eventually my error will be small enough. And so in this case, it turns out there will be a pattern that's relatively easy to identify, but sometimes there's not, and that's okay. You can still just write out enough values until your error is small enough. And so here on the left, then, I'm going to write the derivative of the function, and then on the right, I'm going to write out the max of that derivative in absolute values. And so it'll also be helpful to keep track of which value of n each one of these is. And so when n is equal to 0, for example, I'm taking the 0th derivative, and so that's just the original function. And the maximum of this function, which is ln of x, on the range from 1 to 9/8, is just going to be ln of 9/8, because the natural log is an increasing function. And so in this case, that's not a particularly useful bound for the error because, again, that's a bound that's in terms of the number I'm trying to estimate to begin with. And so that's not going to help me. But I can now start taking derivatives of the natural log. And so the first derivative is 1 over x. The second derivative is minus 1 over x squared. The third derivative is 2 over x cubed. The fourth derivative is going to be a minus 3 times 2 over x to the fourth. And let me write out one more. The fifth derivative would be a 4 times the 3 times the 2 over x to the fifth. And now I need to figure out the maximum of these derivatives in absolute values. And so because we're talking about absolute values, I don't care about any of the negative signs. And so if you ignore them, then you can see that all of these functions in the derivative column are decreasing functions as x gets bigger. And so that means that the maximum of all of these is going to happen when I plug in the smallest x value possible in my range, which is just x equals 1. And so the maximum for the first one will just be 1. The second one will be 1, again keeping in mind that I'm taking the absolute values here. And then I'll have a 2, and then a 3 times 2, and then a 4 times 3 times 2. And then you could guess what the pattern would be. Of course, the next one's probably 5 times 4 times 3 times 2, and so on. And so this is really equal to 4 factorial, 3 factorial, 2 factorial, 1 factorial, and 0 factorial. And so now I want to be able to write that in terms of n. And so if I compare that to the first column here, you can see that really I end up with n minus 1 factorial. Now I can plug this into the error-bound formula that I had written above and try and simplify it a little bit. And so if I go back to that error formula, then I know that Rn of x is going to be less than or equal to. And so here I cared about bounding the n plus first derivative. And so I found that every time you are bounding a derivative, it's really 1 minus that factorial. And so in this case, because that's an n plus 1, I can bound that derivative by n factorial. And now I can simplify this numerator that I had up here. And so that's really a 1/8 to the n plus 1. And so I'll move that down to the denominator here. That's an 8 to the n plus 1. And then I still have that n plus 1 factorial. And now the n factorial here cancels mostly with the n plus 1 factorial down there, but it just leaves that one factor of n plus 1. And so at the end of the day here, I get 1 over 8 to the n plus 1 times n plus 1. And now I know that I wanted to approximate the natural log of 9/8 to within 3 decimal places. And so that's the same as saying that I want this to be less than or equal to 10 to the minus third. And so this is the same scenario as the previous problem that we just looked at, where there's not a great way to solve for n in this inequality. And so the best option here, unfortunately, is to just plug in a few values here. And so I'll do that here, where I'll plug in different n values, and I'll write a table again. So we'll consider plugging in n equals 1, 2, 3, and so on until we get a good bound for this into the expression 1 over 8 to the n plus 1 times n plus 1. And so if I plug in n equals 1 here, then I'm going to get 1 over 8 squared, which is 64, and then times n plus 1, which here is just 2. And so in this case, that'll be 1 over 128. And so that's not quite big enough here. If I look at the next term, though, when I plug in an n equals 2, then I'll get a 1 over 8 cubed times 3. And so if I write out 8 cubed, that's 64 times 8, which ends up giving me a 512. And when I multiply that by 3, then that's roughly 1,500. And so this is less than 1 over 1,000, which is what I was looking for, because 1/1000th is 10 to the minus 3. And so it turns out again that this approximation converges really quickly, and I don't need to go to that many terms before I get a good approximation. And so now I can just plug in the first few terms, and I know that the natural log of 9/8 is going to be approximately equal to what happens when I plug in n equals 1 and 2 into that series, and then substitute the x for 9/8. And so that should be 9/8 minus 1 to the 1 over 1 minus a 9/8 minus 1 squared over 2. And you could simplify this and get what that value is, but this should be within 3 decimal places of the natural log of 9/8. And so my conclusion here then was that n equals 2 suffices for 3 digits.